Okay, so we are going to look at a practice problem from your discussion worksheet for conservation of momentum. And it is the practice problem that's about the 3 balls of clay traveling toward each other. So 3 balls of clay are traveling toward each other and are going to collide and stick together. One ball of clay, which is 40 grams, is traveling at 4 meters per second at an angle of negative 45 degrees with respect to the horizontal. The second ball of clay, 30 grams, is traveling purely horizontal at 3 meters per second to the left. And the third ball of clay, which is 20 grams, is traveling purely vertical at 2 meters per second. When the 3 balls hit and stick together, what is the resulting motion? What's both the velocity and the direction of this glob of all 3 together? So let's draw what that looks like based on the information that's given. We're told that the first ball of clay is traveling at an angle of negative 45 degrees with respect to the horizontal. So if our first ball of clay, let's say the pink ball, it's going to be traveling in this direction, where this is negative 45 degrees. Okay? It tells us that our second ball of clay is traveling purely horizontally at 3 meters per second to the left. So we can imagine that this ball of clay is traveling to the left at 3 meters per second. I did not write the speed of the first ball. I think it's 4. Yeah, 4. So this is at 4 meters per second. And then it tells us that the third ball of clay is traveling straight up at 2 meters per second. Well, it just says vertical, but it's a positive 2, must mean in the positive direction. So you can imagine these 3 balls coming together and colliding, and then something happening, their motion continuing in some capacity, or maybe it comes to 0. We'll find out. All right, well, if these 3 balls are interacting with one another, this becomes our system. So I can draw a circle around the system, and I will identify for that system that momentum is conserved. The initial momentum is going to equal the final momentum. Now, it's very important for us to remember that momentum is a vector. That means that we have to worry about things traveling in 2 different directions. Well, if the system momentum is conserved, and if we think back to the idea of how we found that in the first place with the net force being 0 with those Newton's third law interactions, we know that forces are independent in the horizontal and vertical, as are momentum. So we not only know that the initial and final are conserved, but we also know that that means the initial momentum horizontally is equal to the final momentum horizontally, and the initial momentum vertically is equal to the final momentum vertically. We can separate these momenta into their components, analyze them independently, and then put them back together, just like we've done with forces and with motion. It's all the same physics, which is kind of cool. All right, so let's look at those directions independent. If we're going to define an initial and a final for horizontal and vertical, I have to define what initial and final is. So I have my initial situation represented right before they collide. My final then is going to be right after they collide, such that that collision is represented by that interaction, that equal sign that we talked about in the conservation idea. Okay, so let's look at those independent. We know that the initial momentum horizontal of the system is equal to the final momentum horizontal of the system. I have 3 objects in my system, which means I have the initial momentum of object 1 plus the initial momentum of object 2, and these are all horizontal, lots of subscripts, plus, I'm just going to leave these open, the initial momentum of object 3 in the horizontal. That's going to equal the final momentum of object 1 horizontally plus the final momentum of object 2 horizontally plus the final momentum of object 3 horizontally. Okay, well now let's pull these apart. We know that the initial momentum of object 1 is the mass of object 1 times the initial velocity of object 1 horizontal. The initial momentum of object 2 is the mass of object 2 times the initial velocity of object 2 horizontal. And the mass of momentum of object 3 is the initial momentum of mass of object 3 times the initial velocity of object 3 horizontally. Subsequently, we can do that for our final momentum. The final momentum is mass 1 v final 1 horizontal plus mass 2 v final 2 horizontal plus mass 3 v final 3 horizontal. Now, we know, because they stick together, that the final velocity of 1 horizontal equals the final velocity of 2 horizontal, which equals the final velocity of 3 horizontal. So we're just going to call that v final horizontal. All three are the same. They're stuck together, moving together. So that simplifies things a little bit for us. It tells us the mass 1 v initial 1 horizontal plus mass 2 v initial 2 horizontal plus m3 v initial 3 horizontal is going to equal, all of these velocities are the same, mass 1 plus mass 2. This is the idea of an inelastic collision. The masses combine and they all move together with one final velocity. Okay, perfect. We have all this information. We can solve for the final velocity. Mass 1 is given as 40 grams, so 0.04 v initial horizontal. Well, this one's moving at an angle. So how do I get the horizontal velocity? Well, this is v initial horizontal for mass 1. So that is the velocity times the cosine of the angle. So 4 times the cosine of 45, 2.83. Plus mass 2, which is given as 30 grams, so 0.03, times v initial of mass 2. Well, that's moving to the left at -3. Plus mass 3, which is given as 20 grams, so 0.02. Well, that's moving purely vertical. So that has an initial velocity in the horizontal direction of 0. That is going to equal the sum of my masses, 0.04 plus 0.03 plus 0.02 times my initial horizontal velocity. So I can then solve for my initial horizontal velocity. My final horizontal velocity, the velocity of the glob in the horizontal direction, by simply doing the algebra. So we have 0.04 times 2.83 plus 0.03 times -3. We have to pay attention to direction. Plus 0 divided by this sum, 0.04 plus 0.03 plus 0.02. And I find my horizontal velocity equal to 0.258 meters per second. All right. Well, that's only in the horizontal. So we also have to consider the vertical. But we can do the same thing vertically. We know that the P initial vertical is equal to P final vertical. Momentum is conserved. It's conserved in the independent directions. So that's P initial of object 1 plus trying to keep my colors the same, in the vertical direction. P initial 2 vertical plus P initial 3 vertical. And that's going to equal P final 1 vertical plus P final 2 vertical plus P final 3 vertical. And like we did for the horizontal direction, this is M1 V initial 1 vertical plus M2 V initial 2 vertical plus M3 V initial 3 vertical equals, and this is just the definition of momentum, M1 V final 1 vertical plus M2 V final 2 vertical plus M3 V final 3 vertical. And similarly, we know that V final 1 vertical equals V final 2 vertical, which equals V final 3 vertical, so we're just going to call it V final vertical. They stick together, they move off together. So I can rewrite this to represent M1 V initial 1 vertical plus M2 V initial 2 vertical plus M3 V initial 3 vertical equals M1 plus M2 plus M3 all times V final vertical. Okay, now let's plug in the information that we know. M1 is 0.04, and now we're interested in V initial vertical. So that is the sine component of negative 45, so we have 4 times the sine of negative 45, which is equal to, I should have known that, negative 2.83. It is pointing down. Plus 0.03 times, well, it's only moving horizontally initially, so that's 0, plus 0.02, and it's moving up at 2 meters per second, so that's positive, is going to equal 0.04 plus 0.03 plus 0.02 times the final vertical. And similarly, I can do the appropriate algebra, and I find that V final vertical is equal to 0.04 times negative 2.83 plus 0.02 times 2 divided by 0.04 plus 0.02 plus 0.03. And I find that V final vertical is equal to negative 0.813 meters per second. And we're interested in determining the resultant velocity. So I have a horizontal component and I have a vertical component. So V final is going to equal the square root of V final vertical squared plus V final horizontal squared. And that equals squared plus 0.258 squared, 0.85, that's the right 0.8. But I also need the angle, which is the inverse tangent of V, this marker is dying, initial, final vertical over final horizontal, and the inverse tangent of that is negative 0.08. Oops. 813 divided by 0.258, negative 72 degrees. All right, good. So, recognizing that we have a collision, momentum of the system is conserved in that collision. So we examine that conservation principle, defining what's the initial right before the collision, what's the final right after the collision, recognizing that momentum is conserved in the individual components. So we recognize that the horizontal momentum is conserved, the vertical momentum is conserved. As we follow through that process, looking at each momentum of each object within the system, we recognize the type of collision we have, and we can simplify the math and solve for our individual components, putting them back together like we always have with both the magnitude and a direction. All right, good job.